is chapter 7 or 8?
This is chapter 7. We're pretty much just kind of moving really quick through chapter 7. We're not really going to look at chapter 8. Chapter 8 is some acid-base stuff. We're going to skip chapter 8 and move straight on to chapter 9, which is the stuff that's more relevant to our conversation. Chapter 9 is electrochemistry. And so we'll be dealing with the movement of ions in solution and the free energies of ions going into solution. That stuff will be fun. So just kind of throwing together some of the conclusions that we can draw from the values of K. If delta G of the reaction is negative, then our K is going to be greater than 1 and products are going to be favored in the reaction. If the delta G is positive, then K is going to be less than 1 and the reactants will be favored. And so all of that is going to be, whether or not delta G is negative or positive is going to be a function of what the concentration of our products are, what the concentration of our reactants are. We can look at the expression for delta G. Delta G is delta H minus T delta S. And you've probably already done this little bit of exercise in Gen Chem, but we'll just do it one more time for the sake of practice and reminding ourselves. If you've got a delta H for a reaction that's negative and a delta S that's positive, then the delta G of the reaction is always going to be negative. And so K is always going to be greater than 1 at all temperatures. If you have a negative delta H, so this is a heat releasing reaction, and you have a negative delta S, then you'll have a negative delta G if your temperature is less than delta H over delta S. Right? So we can solve for that just by establishing delta G as negative and deciding what value of T you'd have to overcome what value of T you'd have to make this negative term greater than that positive term. Yeah. And if you got a positive delta H, then it's still possible to have a spontaneous reaction, a negative delta G. If you have a positive delta H and a positive delta S, but now you just have to pump the temperature up high enough that T is greater than delta H over delta S, and then the entropy term will dominate, and you'll still have a spontaneous reaction. And if you've got a positive delta H and a negative delta S, then in that case, both of those terms in the delta G expression are always positive, and so you have a reaction that is that's never spontaneous. And just to remind ourselves what we're talking about, the delta G expression was derived taking a look at the entropy of the system and the surroundings. If you've got a negative delta H, this is a reaction that's dumping heat off into the surroundings and therefore increasing their entropy, right, increasing their disorder. And if you have a positive delta S of the reaction, that means that the reaction itself, or the system itself, its entropy is increasing. And so a negative delta H and a positive delta S is the situation where a reaction is increasing the entropy both of the system and the surroundings, and that's why that guy is going to have a negative delta G at all times. It's always going to be spontaneous, right? When you have a negative delta H but a negative delta S, that's the case where you're dumping heat off into the surroundings, increasing their entropy, but at the same time, the entropy of the system is decreasing if delta S of the system is negative. And that's why we've got to choose our temperature correctly so that we can still keep the total delta G negative. Okay, and the same things can be said about scenarios 3 and 4. Positive delta H, the entropy of the surroundings is decreasing, and so we have to account, we have to try to make delta G positive by having a sufficient increase in the entropy of the system. Yeah? All right. So that is that piece of information. So I'm not going to do this, I'm just going to show it to you. It's in your book. You can trace back. You can go back and look at the book and see their derivation. But you guys have all seen how these K equilibrium constants K are used in ice tables with acid-base equilibrium, right? We can use the known value of K and then known starting conditions of concentrations of our reactants or products to figure out which direction the reaction is going to move in before equilibrium is reached. They give an example where they use the synthesis of ammonia. You had nitrogen and 3 hydrogen molecules coming to equilibrium with 2 moles of NH3. They say that the K for this reaction is 977. So once you've got K established, you set up your ice table, you write in your initial concentrations. In this particular problem, they had ammonia, or had nitrogen at 1 bar, hydrogen at 3 bar, and ammonia at 0 bars. That's your initial concentrations. Change is minus, name a variable, we'll call it X. So if X pressure units of N2 go away, then also 3x pressure units of H2 go away, and we gain 2x pressure units of NH3. And so at equilibrium, our pressure of N2 is 1 minus x, H2 is 3 minus 3x, and NH3 is 2x. We set that up for our K's. K of pressure, I should put a little p right there, we get 2x squared over 1 minus x times 3 minus 3x cubed due to the molar coefficients in the balanced equation. And you do a bunch of math, you end up placing this thing in quadratic form, you plug in the quadratic formula, and you're going to get 2 roots. And the way this works out is that, there's a little bit cut off here on the side, sorry. The way this works out is that one of those roots is going to lead to an answer that is real, as with respect to the parameters of our problem, and the other answer will give you answers that are not real. For this particular one, they ended up getting x is either 1.12 or x is 0.895. We know that if the equilibrium pressure of nitrogen is 1 minus x, then x can't be 1.12 because then you have a negative pressure for nitrogen, and that just doesn't happen, not in this reality. And so you end up choosing the number that makes sense for your problem. Choose x as 0.895. We plug in the values, and we can solve for our equilibrium pressures. We find that nitrogen ends up being at equilibrium at 0.1 bar. Hydrogen goes to 0.32 bars, and NH3 goes to 1.8 bars. Yeah?
How are you going from the basic quadratic formula to that one below it with the g's?
You have to go back and look at the book. I just chose the example from the book because it would be the easiest for you guys to go double check. It's right there in the text. But you end up, when you try to simplify this thing, you end up with an expression of square root of 27 times 977 over 4 that sits right out in front of one of your terms. And we just kind of group that all together and just call it G, just for the sake of not having to rewrite square root of 27 times 977 over 4 10 times in the problem. And then you end up with the quadratic form gx squared minus 2g plus 1 times x plus 1g, just 1g.
Okay.
And so that becomes your a plus b plus c form, and you just plug in those values, g for a, 2g plus 1 for b, and 1g for c, into your quadratic form, and end up with those answers. So the reason I showed that to you is that chances are I'm going to give you a homework problem that asks you to do that. So just a quick reminder that that's what we're trying to do. So now we're going to have a conversation again, or a conversation that we had one time before, early on in the semester, when we were talking about the Boltzmann distribution. It's observed, we've, had, we looked at Le Chatelier's principle, that if you end up with heat on the product side of your equation, that an increase in heat will shift the reaction towards reactants, right? And so the whole system acts to minimize the disturbance. So if heat is one of your products, you just increase the amount of heat, you drive it back towards reactants. If heat's one of your reactants and you increase the heat, you drive it towards products. We didn't really talk very much about why that was. We just, kind of waved our hands and said it was because of Le Chatelier's magic. The system wanted to, respond to minimize the disturbance. But when we talked about the Boltzmann distribution of molecular speeds, what did we say? We said that when we increase temperature, we increase the total amount of energy that the system has, right? And so at a finite number of molecules, if the energy increases, then the distribution has to shift towards the higher energy states, right? To accommodate the energy. We have to start populating higher energy states in order to accommodate the total energy available in the system. So if you take a system of gases at one temperature, and their curve looks, the Boltzmann distribution curve looks like this, at T1. If we go to T2 is greater than T1, then we're going to shift that distribution to higher speeds, right? Just because we have to have our molecules on average moving faster to accommodate the increase in energy that we delivered when we increase the temperature. Yeah? Well, here, we're going to kind of look at this equilibrium system of reactants and products in a similar way. Our reactants molecules and products molecules are a way that our system has for storing energy. You increase the temperature and, on average, maybe their velocities will start growing. But another thing that will happen is that the distribution will shift towards whichever species are higher in energy. So if your reactant molecules are higher in energy than your product molecules, what kind of reaction is that? Or reactants are higher in energy than products? If reactants are higher in energy than products, heat will be released, right? Exothermic reaction. So if we have an exothermic reaction where our reactants are higher in energy than our products, if we increase the total energy of the system, if the system is an equilibrium system, where there's a readiness to move between one kind of species and another, then the species with higher energy will be populated. And so increasing the temperature on an exothermic system will shift the distribution of molecules towards the higher energy reactants, which is the same thing that Le Chatelier's principle told us. Temperature or heat is a product of the reaction, increase the heat, drive toward reactants. Well, heat was only a product of the reaction in exothermic reactions, right? So you increase the heat, you've got more energy distributed through the system, the equilibrium is going to shift towards the higher energy reactant molecules. If the system is an endothermic reaction where the product molecules are higher in energy than the reactant molecules, then you increase the heat, increase the total amount of energy that has to be stored, and you're going to shift the distribution towards the higher energy product molecules, right? And so an endothermic reaction where heat is a reactant, you increase the heat, you drive it towards products. Yeah? Your text gives you a diagram that looks like this. The white bars, as I've drawn them, represent the available energy states for the, what is this? Reactant species. I was supposed to have drawn a label to show which ones are reactants and which ones are products. So the species in black are the product molecules, energy states. The species in the bars in white are the reactant molecules, energy states. We see that this is as drawn, represents an endothermic reaction because the energy, the relative energies of the product species are higher than the reactant species. In general, it'll tend to be that that your lower energy species are dominant, and because the energy levels of the lowest energy states get populated first, just like they did with the Boltzmann distribution. And so it'll tend to be that the lowest energy species, in this case, our reactant molecules, will end up dominating the equilibrium. But as you shift the temperature, as you increase the temperature and more energy is delivered to the system, you'll end up pulling molecules out of these lower energy states and populating the higher energy states. Just like we learned to predict using Le Chatelier's principle. It is always the case that an increase in temperature is going to shift the distribution towards the higher energy species. It's not always the case that the lower energy species are going to dominate the equilibrium mixture. Your text also gives you an example, graphical representation of when that's true. This image is almost exactly like the image above it in that the product species are higher in energy than the reactant species. But in this case, the spacings between energy levels between the reactants and the products are different. The spacing between energy levels of the reactant species is very large, and so the first excited state of this reactant species is way higher in energy than the ground state, and the next excited state will take a big jump in energy. For the product species, that's not the case. The product species have close energy spacings. It turns out that species that have close energy spacings are species that have high entropy, and so when you get really close groupings like that between the energy levels of a particular reactant or product, that correlates to those species having a high entropy. And you'll see that maybe at very low temperature, we might have that all of our species are in the ground state, and so at low temperature for this reaction, our reactants will dominate. But as we increase the temperature on this guy, we have to start populating the higher energy states, and it might be that, at the point that we've filled this energy level, we've accounted for all of our energy, and in that case, we would have more species in our products, in our high energy products, than we would have in our low energy reactants. And so the way that you can think of this, what you can think of this as representing, or as suggesting, is that the species with the highest entropy ends up dominating at high temperature. Does that ring a bell? Do you guys remember any other time where we discussed species with high entropy being dominant at high temperature? Remember when we drew the Gibbs energy curve of the solids and the liquids and the gases as a function of temperature? So it was Gibbs free energy versus temperature. And we had a bunch of curves. We had the gas curve, the solid curve, and the liquid curve. So this was solid. This was liquid.
Yeah, exactly.
And this was gas. And the slopes of these guys went as negative s dt, right? So if we had t on this axis, the slope of each curve was proportional to s, and we found that because the gas had the largest entropy, that at high temperature, the gas phase was favored. Well, that's kind of the same thing that we're talking about here with our multiple species system, with our equilibrium system. We're not talking about one species with 3 phases. We're talking about these multi-molecular systems. But essentially, what this is suggesting is that whichever species whichever side of the reactions or products, has the highest entropy, that side of the reaction is going to end up dominating at a high temperature. It's going to be most favorable at high temperature. I didn't have a chance to draw everything that I wanted to on the slides today, but try to copy something that's came from the text real quick over here. The text gives you an example of this. It gives you Gibbs free energy versus temperature curve. 3 different reactions. Reaction 1 is carbon monoxide gas plus 1/2 O2 gas goes to CO2 gas. The other one was carbon solid plus O2 gas goes to CO2 gas. And the other one was solid carbon plus 1/2 O2 gas goes to CO gas. In here, in this top reaction, you've got you've got 1.5 molecules of gas going to 1 molecule of gas, right? So what's the sign of delta S for this guy?
Negative.
This guy has a negative delta S for that reaction as written, in the direction written. This guy, you've got 1 mole of gas on this side, 1 mole of gas on that side, and so delta S is approximately, but not exactly, 0. Right? Over here on this reaction, you've got a 1/2 molecule of gas going to 1 molecule of gas. And so this guy, you've got a positive delta S, right? And the curves just communicate what the Gibbs free energy of the reaction is in the direction written with respect to temperature. This guy, where delta S was decreasing, which had a negative entropy, as you increase the temperature, the Gibbs free energy increases in sign, meaning that it's less spontaneous, right? This reaction in the middle that has approximately delta S is equal to 0, you increase the temperature, and the Gibbs free energy of that process doesn't change at all. It stays constant. And then down here, for this reaction that has the positive delta S, you increase the temperature, and the G of that reaction ends up, I should say delta G of that reaction, ends up lowering with an increased temperature. So that's just another way of looking at what we just said. We said that reactions that have a high entropy change, a high delta S, or a positive delta S, if you increase the temperature, those reactions become more favorable. The delta G becomes lower at high temperature for those reactions. Another way to look at this, yet another mechanism for thinking of this, is in terms of the Van Hoff equation. And we derive this expression. It says the natural log of K is equal to negative delta G naught of the reaction over RT, right? And this can be broken apart because delta G is delta H minus T delta S. We get the natural log of K is negative delta H over RT plus delta S over R. And we're going to make an assumption here for a second. We're going to say that we're just using a very, very small change in temperature, and that over the change in the temperature range that we're moving through, we're going to say that delta H and delta S are relatively constant. And so we'll recast our expression for the natural log of the equilibrium constant at some new temperature, T prime. And so we can write that natural log of K prime is equal to negative delta G naught over RT prime, which is equal to negative delta H over RT prime plus delta S over R. And you'll notice that the only terms that change are the ones that have the temperature dependence, because we said delta S is doesn't respond to a change in temperature, it's constant over temperature. And these two terms are exactly the same. And so we simply subtract natural log of K prime from natural log of K. It's the equivalent of taking this term and subtracting from that term. And we end up with an expression just like this. Natural log of K prime is equal to natural log of K prime is equal to natural log of K initial plus delta H over R times 1 over T minus 1 over T prime. I'm just going to double check and make sure I didn't screw that one up. Yeah, that looks like it's right. And so this just predicts the same stuff we just talked about. You got T prime down here. If this is an increase in temperature, then this whole term is positive, right? If 1 over T prime is smaller than 1 over T, meaning that T prime is greater than T, then this whole term is positive. So if we have a positive value here, then the sign of delta H of the reaction determines whether or not K prime is going to be greater or smaller than K, right? If this is negative, then there'll be then K prime will be smaller than line K. If delta H is positive for that reaction, then K prime is going to be larger than K. A positive delta H, of course, correlates to an endothermic reaction. And so what we just said is that if you increase T on an endothermic reaction, you end up with a larger K, right? K is the equilibrium constant. The reaction is endothermic in the direction written, and you raise the temperature, you're going to push it towards those high energy products. You get a larger K value, larger value of the equilibrium constant. If delta H is negative, as it is for an exothermic reaction, then increasing temperature, this will be positive, this will be negative, will end up decreasing K prime relative to K. So we've got an endothermic reaction, we increase the temperature, we've got an exothermic reaction, we increase the temperature, and we push that reaction back towards the high energy reactants, thus decreasing K prime relative to K initial. So that's just like 6 different ways of cooking the same goose right there. All right. Now, one more bit of logic for you before we run out of here. And this gets back to that pressure dependence stuff that we were looking at for our equilibrium constant. This is also given in your text. I feel kind of